Thanks for your patience. I'll give you that 3 minutes back at the end if you want it. No one cares. All right. So today we are going to hear about accuracy and speed from Eduardo, who's super prepared and ready. Good. And you're also preparing your second homework. And that means you finished your first homework. And you're really happy with it. And you definitely have comments in there. And you describe why you think it worked. Right? Okay. So let's start off. Any questions about the homework so far? I mean, the stuff that we did last week. It's graphics and visualization, but really, it's sort of slicing and understanding arrays and some plotting. A lot of this class will be plotting in order to understand our results. We'll talk about accuracy and speed today. No class on Monday, but also no homework. Oh, amazing. We love it. Okay. So I'll start going through, and if you feel like something is not quite done, you can always write a note at the very top, say, hey, I'm not quite done with this, but I'll start leaving comments in your work. Okay. So if you go back and you look, you'll say, oh, wait, this section here, it'll say MC : and then I'll write some words in your code. Does that make sense? And I might even throw a snippet of code, right? If I see like just a small error, I'll just write the same line, but comment it out, and you'll see what the improved version of that code will be. Okay. Questions, comments, concerns? All right, let's get down to business. Oops, let's get rid of that. All right. Eduardo, where do you want to start? 126. Probably of the textbook itself.
So this is the beginning of the type of part. The title is accuracy and speed. So we'll be talking about like significant figures, about numerical errors within the program, and we'll talk about speed, which is maybe 4.3.
Yeah, we might get up there. Yeah.
So to get started, we have what have we learned so far? Some of the basics that we learned in Python are the input, output, variables in arithmetic, loops and ifs, loops and if statements. And we did a lot of calculations with those, but have we ever encountered a limitation when we were using those? I did not, but computers do have, or the program Python does have limitations. There is a number that is too big, and one that is too small that Python pretty much caps it. Normally we don't come across these ranges. And the computer runs quickly and accurately. Nevertheless, if we do come across these limitations, the computer will do some interesting changes, and we'll learn how to deal with them. So the 4.1 variables and ranges. So some variables that we deal with are integers, floating points, complex variables, and lists and arrays. Python, they're able to hold, the Python variables are able to hold a large number, but not that big. For example, float points, the highest recognizable number is 10 to the 308.
And just to clarify, right, that is pretty big. That's really big, right? Generally speaking, what kind of physical object would you consider is 10 to the 308th? It's like size of a galaxy. What's the order of magnitude in like meters? Do you know? Ten to the 15, 10 to the 16. Size of the universe. Maybe 10 to the 20, 10 to the 25. So these numbers here are gargantuan. You think to yourself, well, what about the economy? right? All of the money that exists everywhere, that's like trillions. So that's 10 to the 12. That's not quite big enough, right? Astronomical, all of the atoms, grains of sand on a beach, 10 to the 26, right? This is a substantial number that if you run into it, you probably made a mistake. Okay. Yeah, right. This is very, 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 very big.
Same with like the smallest number is 10 to the negative 308.
And similarly, right? Too big. Okay.
Then we have, it talks about another example with complex numbers, both real and imaginary numbers. They both also cap at, plus or minus 10 to the 308. There's also a limitation there with complex numbers. Something to know, the scientific notation E, it's always a flow. So something to know. For flow point, when we exceed 10 to the 308, when we actually exceed that cap, it is said to overflow. And if we drop below 10 to the negative 308, it is said to underflow. But what happens when we actually go beyond these limits when we on Python? Interestingly, no error will be produced when we run the program. For example, if you have like y is equal to 10x, like this, it says right there, where x is pretty much a number close to that limit, and multiplying 10 would give you beyond that. So what would produce for the y, you would still run it, but you would change that number to INF, which would mean infinite. And so if you were to print out that value, it would be INF.
That makes sense. So let's think about why this is happening for a moment. Again, we talked about lockers, right? And each one of these lockers holds information. It either holds a 0 or a 1. And that's how the computer stores information. Well, your memory is fixed. Just like in your brain, you can't remember everything. The computer can't remember everything. So that's why we have, conversations about how much RAM you have, how much storage you have, etc. Right? Those are physical limitations. And so when we think about how much memory is set aside for a number, there's a certain number of those lockers that can hold zeros or ones. And if you create a number that's larger than 10 to the 308, that means that you have filled up all of the lockers. And now the computer doesn't know what to do. And so all numbers greater than that are equal to the same number, which is basically a form of an error warning, which says infinity. Does that make sense? People get that? Okay.
So that's only for floating numbers, right? So
Mhm.
float point.
Mhm.
Yeah, for the next point that it talks about are integers. So when it goes under and it's way too small, it'll just go to 0.
Yeah.
Very good. And then talking about integers. Yeah, so what about integers? For integers, there is no cap as long as you have enough memory space to store the digits. So as long as you have a computer that has like so much memory in there, you're able to just get started. So your cap is the amount of memory you have.
Which is good and bad because you can use up all the memory, right? Okay. Cool. Hold on. Let's pause there. I think the first pair programming is right here, right? Yeah, 4.1. So let's do 4.1 and then we'll have Eduardo, if that's okay, we'll come back and we'll do 4.2. We'll talk about speed and we'll do exercise 4.3. Is that reasonable? Because I want to show people that this is actually, this is not a very long process. We're going to try and break the computer. That seem reasonable? Yeah, let's do it. Let's treat those rocks. Okay. So let's pair up. I'm going to pause the recording so that we can come back to it.
Which is the decimal representation of the binary number 2 times 10 to the 1024.
2 times 10. Okay, right.
Or sorry, 2 to the 10 to 10. I'm not clear.
Yeah, so this is 10 to the 24. So you may not be familiar with what this symbolism is. 2 to the 1024 is how many bits are represented in your locker. So there's 1024 bits of information. That's 1024 information locations. So 0, 1, 0, 1, 0, 1, that type of math, right? And so because each 2 can be either on or off, and they can be in any various combination, you'll remember combinations from math methods, it'd be 2 to the number of combinations, 2 to the K. So if you had a smaller transistor, let's say you only had 2 lockers, right? 2 to the 2 would be 0, 0, 1, 1, 0, 1, 1, 0. 4 combinations possible. As soon as you add another locker, now you have 3 lockers. How many individual combinations can you have? What? If you flip those numbers, so 2 to the 3 is 8. So it's 2 to the 2, 2 times 2 times 2, right? And then you keep adding 2's on and on and on until you get to 1024, which is the standard memory unit for. C'est bon? No, not delicious. Is it good? Does it make sense? Okay, cool. Should we go on, Eduardo? Cool.
Talk about how calculations can affect the speed of the computer, but now how do we get numerical errors? So this portion will deal with numerical errors and how we deal with them, which are mainly seen when we start rounding off the numbers. And so with integers, we don't have to worry about this since we can store every digit and do calculations, assuming that you have like the same data type and the same memory and fast enough computer to do the calculation. But the problem is with this, the floats, the floating point numbers, because it has a certain precision, and a precision is another word for significant figures or how many digits we include in a given number. And so the standard precision for Python is 60 significant figures. So for example, we take 5, it would round out at the 16th significant figure. And so you have the true value of pi and then the value of pi in Python, and the difference of it would be your error.
Is that reasonable for folks? So typically this won't matter, right? If you're doing something like calculating the area of your pizza, you're fine, right? But if you're calculating, say, the area of the sun, which might have 10 to the 16 multiplied here, right? In meters or something, and you want it really precise so that your spacecraft doesn't fly into the sun and maybe just goes really close to the sun, it might matter significantly, right? So we want to think about these errors very seriously. Okay, go ahead.
So a number does not need to be irrational to suffer from this numerical error. As long as the number is more than 60 significant figures, it will just pretty much round off. These mean that our calculations in Python will be guaranteed accurate to that 60 significant figure.
Okay, and I'll pause you here. So for folks who are following along, if you haven't done this already, this is really fun, okay? So as he talks you through this, go ahead and put these numbers in, right? So you add 1.1 to 2.2. What do you expect to get? What? 3.3. That's your expectation, right? That's everyone's normal standard math. But sometimes you'll get this. Is that the same?
I was actually yesterday, and it gave me 3.0000.
Okay. You got this number?
No, I got.
Yeah. Why? I don't know. It's fucking whatever. That's numerical error at work, right? And, you know, Eduardo's going to talk about this more in detail, but this is really a time for you to think about the computer, not simply as something that listens to you, right? Because it doesn't listen to you. It does what you want it to do, but it's limited by the fact that it's rocks. So we really want to, in this section of the class, now that we've sort of learned some of the basic tools, we want to see how those tools are limited by the fact that it's hardware, right? And that we don't have infinite precision. We don't live in the future. Well, we kind of live in someone's future, but in the future, maybe all of our computers are like ethereal things that like have infinite memory, quantum computers. That's not where we live yet. I might have to reteach this class in 20 years, but that's not now. Okay.
Yeah, so for this reason, if we should never use an if statement to test the equality of two floats. Like you have like yeah, if x is equal to 3.3, and if you were to print out x right there, it would never print out x because it recognizes the 3.2999 is not equal to 3.3.
Right. You see why that is? Cool.
So this numerical error that it has does affect when you're doing the equality of floats or two floats.
Is this affected by in integer math? Yeah, you're right. You're right. But why is that? Why do, if I have x equals 3 as an integer, why is it the case that that's okay, but x equals 3.0 is not okay? What's special about integers? What did I just make you do in exercise 4.1? What's that? Yeah, they're exact up to a very, very large number, right? There's no decimal places. When we're talking right now, right, about what Eduardo's talking about, saying 3 and 0.2999 repeating, they're not the same number. But 3 and 3 are always the same number, right? In the computer. There's no room for modification as long as you don't put a decimal place. Okay.
But if you come across a column that needs you to test the equality of floats, what do? Like, so there is an actual way to attack this, and so there you have a data type a variable epsilon is equal to 1 to the negative 12. And so if you make an if statement where you have that absolute value of the difference between the 3.3, the one that you actually get, the 3.2999 minus 3.3, it will take the absolute value of that, and if it's less than the epsilon, it'll actually go through and up.
That makes sense? Kind of. You want to see it slowly on the board? Yes, sir. All right. So let's take the number 3. Okay. We have 3.3. Let's call that y. Let's call z equals 3.299999. Oh, Jesus. I don't remember how many I did. Okay. What's epsilon mean? Epsilon, usually when we think about it in mathematics terms, that's this symbol. Wait, no, that's delta. Epsilon is this symbol, right? The dot. Oh, like that, yeah. I'm not going to do that right now. We're just going to use this one. And that just means a scooch, like a smidge, okay? So this is a little bit. And 1e to the minus 12, that's small, right? It's like if you took Taylor Swift's bank account and my bank account and you took my bank account, you divided it by Davis Swift bank account, that's the number you get. Literally, right? Billionaire, not a billionaire, right? Okay. So here's the epsilon. So the question we're having here, if I take the difference between these two numbers, so this would be x or y versus z instead. What number are you going to get? What is y versus z? In a perfect world. What's that? Well, like if you look at the way that I've actually written them. You're right, but what I've written, not what I meant to write. Yeah, it's okay. So if I take this number and I subtract this number, what do I get? What? 0.1 probably. So let's go through the threes. Yeah, that's a 0. This one. What? No, because I have these 9s, remember? Right? I get a 0, 1. Right? Then I get a 0 here. I get a 0 here. And I have to count all of the zeros. And then a 1. Right? And how's that represented on the computer? Is it represented like this so foolishly? No, it's not. Probably. No, computer's smarter than Mateo. So what do we write here? We write 1e minus boom. Okay. So that's how it's represented on the computer. You took those two numbers, you took the difference. And then the question is, if this number is smaller than whatever your scooch was, then print it. Right? Helpful or not? Okay, let's go. Let's go.
So to add a note on that, like the 1e to the negative 12 is an arbitrary number. Like you don't have to use that. You can use another number. Maybe you want to use a number that's more appropriate to the specific problem that we're dealing with. All right, so now we're introducing epsilon. So epsilon is the rounding error, which is the amount we would add or subtract to the value to get the true value. So basically what we were talking about earlier with the pi, the difference, that'll be your epsilon. So we have an example with x is equal to this value for 2. There you have so you have there x is equal to the square root of 2. But you want to import, so because Python would take the square root of 2 up to the 16th significant figure, we want to incorporate the error. So we add epsilon. So it's x plus epsilon would give you the actual value of the square root of 2. So to figure out x, it's like epsilon to x is equal to the square root of 2 minus epsilon. And so that value, it turned out that in the real world, this is the same definition for the rounding error in mathematics experiments. For example, like the age of the universe being 13.8 plus or minus 0.04 billion years. It'll give you like that same type of error. Or it will incorporate the epsilon would be like that error.
Okay, so let's pause here for 1 second. Do we trust that this really is going to not be correct? You all have your computers in front of you? So find out what x is, print x. What'd you get? 1.4. 1.414, and it goes on. And then b goes on and on and on. So what happens if you square it? Yeah, call a x quantity squared, right? X times x. And then print a. What do you expect to get? Let's call x the square root of 2. And then let a equal to x times x. I expect to get, right, I expect to get this, right? Is that what I get? There's a 4 at the end. I don't know, it's kind of a 4. You see? So even in the most simple calculation we can think of, you get a 4. And now it's a 4 at the end, right? So like maybe that's not so important, but it might be important. Okay. Yeah. Oh no. Okay, we're not going to go through this in a super ton of detail, because it's better to just do it. I think we're going to do calculating the derivatives. And if you don't love derivatives, I've got really bad news. Okay. I think that's about where we want to stop for today. If that's okay. And here's what we're going to do. We're going to talk about what it means to be a derivative. Now, for some of you, you already know, and you're going to be like, this is boring. And then we're going to make the computer calculated derivative. And you're going to see what it means to go to infinitesimally small. Let me pause this share really quick.